You want the other mode?
No, I don't know.
Okay. Good morning. In name of the organizer committee, we'd like to thank you your presence, your participation with your works, dissemination, and at the same time to contribution for the open discussion in order to improve this topic that is about composite materials. Okay, the first speaker is Kumar Tiwari. Sorry, my error.
Yes.
And the name of talk, the presentation is Refinement of defect detection in the contact and non-contact ultrasonic non-destructive testing of wind turbine blade using guided waves. Please.
Very good morning, Honorable Chair and the researchers. My name is Kumar and I work at Ultrasound Research Institute of Kaunas University of Technology, Lithuania. And I am here to talk on refinement of defect detection in the contact and non-contact ultrasonic non-destructive testing of wind turbine blade using guided waves. So what are guided waves? Guided waves are the ultrasound waves which travels over the thickness of the structure depending on the excitation frequency of transmitting transducer. So this is the basic principle of the ultrasonic NDT using guided waves. Sensor or transducer may be any type. It can be laser, air-coupled, electromagnetic, piezoelectric. It can transmit any waves, pulse, continuous, trip signal, burst signal. It can work in contact or non-contact manner. A single transducer can be used as a transmitter or receiver. It means pulse echo mode. Or two transducer working as a transmitter and receiver respectively, and it is called as pitch catch mode. Or maybe many transducer can be connected together to form a phased array. Transmitted ultrasound wave, when interacts with the composite structures or sample, the ultrasounds can be reflected, refracted. In-plane ultrasound waves can be converted into the out-of-plane or vice versa. So it creates some more complexity. That is why to extract or to measure, to estimate the parameters of ultrasound waves such as amplitude, velocity, resonance, attenuation, we need efficient signal processing techniques or imaging techniques. In this way, we can extract the size, location, or characteristics of the defective signals. So why we need signal refinement or processing techniques to extract the defect parameters or defect features? Why? First, due to the multi-layered structure of composite materials, such as in the wind turbine blade or aircraft wings, and mechanism of the ultrasound guided waves, what I mentioned earlier in the slide, due to reflection, refraction, mode conversion, scattering of the waves, and the less information in B scan and A scans compared to C scan. The most conventional ultrasound techniques, ultrasound NDT technique for the defect estimation is C scan, which is two-dimensional scan over the structure. But if the structure has the complex geometry or only the one side axis is possible, then C scan process will be very time consuming. That's why in this research we are using a single linear scanning or a B scan. But as the B scan has the less information, it needs more signal processing. So how we do? We have to accumulate or combine the various signal processing algorithm to create an efficient algorithm. So these are the characteristics of the transmitting and receiving transducers and the low frequency ultrasonic system. For MFC transducer is working as a transmitter, which is macro fiber composite transducer developed by NASA. It is very thin and compact in size, which can be embedded on any structure, which can be glued, and it is highly efficient transmitter and receiver of the fundamental guided waves. Receiving transducer is a point-type wideband piezoceramic transducer, which bandwidth is -6 dB up to 350 kilohertz, and center frequency of 90 kilohertz. And the parameters of low frequency system is mentioned here. Low frequency ultrasonic system and receiving transducer and all other components apart from the MFC transducer, are developed by Ultrasound Institute, Kaunas University of Technology. So, where to locate the transducer? For example, we are using the excitation frequency. At this frequency, what will be the coverage region of the transducer if we are using only a single linear scanning? So in the previous research, I already developed the 2D analytical model for the directivity prediction of ultrasonic contact type transducer in the generation of guided waves. So we can easily, within 3 minutes of time, without using the numerical modeling and experimental techniques, we can find the location of the transmitter where to fix on the composite structure. So this is the experimental investigation of the sample. Here is the sample, front view and the inner view. This is the MFC transducer. This is the contact type receiver. And this is the inner view. So during the experimental investigation, defect was not visually visible. Here's the schematic of experimental analysis. So you see the transmitter, MFC transmitter, and the contact type receiver is attached to the low frequency ultrasonic system. MFC transducer was excited at 43 kilohertz, 3-period sinusoidal burst with Gaussian symmetry, and the receiver was scanned away up to 180 mm with a sampling frequency of 180 megahertz and a scanning step of 0.2 mm. We received the signals. So the B scan is acquired, experimental B scan, and it is shown here. So we can clearly observe that due to reflection and scattering, there might be the defective region, and there may be the defect-free region. So detection is possible, but location and exact size of the defect and the difference between the ultrasound waves in the defective region and defect-free region is not possible from the experimental results. So for this, we need to develop an algorithm to process the experimental results. So this is an algorithm. First, experimental B scan, we will apply the discrete wavelet transform and amplitude detection technique to locate and size the defect. So in discrete wavelet transform, we will discuss later in the later slide. And then to find the phase velocity, arrival time, and instantaneous amplitude variations of ultrasound waves in defect-free region and defective region, we will apply two-dimensional fast Fourier transform. If we see phase velocity and dominant mode estimation is possible or not. If not, what we do, we will filter out the reflected waves from the B scan. Then the B scans will be generated only from the direct waves. Then we select the A scans in the defect-free region and defective region. Then we will apply the variational mode decomposition technique. This technique, what it does, it decomposes the signal into the monocomponent signals. So the frequencies are not mixed. How it is called? It is called intrinsic mode functions. Intrinsic mode function is defined if the difference between number of extrema of the signals and number of the zero crossing of the signal is maximum differed by 1, means either 0 or 1. So we will discuss. And then Hilbert Transform. Hilbert Transform will be applied to extract the instantaneous characteristics of the signal. We cannot apply Hilbert Transform without using the variational mode decomposition, because we need monocomponent signal, otherwise Hilbert Transform will not work. So this is the denoised B scan after applying the discrete wavelet transform. So we used here Dobitsch's mother wavelet. There are many wavelet families such as Dobitsch's, Haar wavelet, Simlet wavelet. But we selected Dobitsch's wavelet because we did not observe any significant difference while using the other wavelets. But as the Dobitsch's wavelet is orthogonal in nature and more energy preserving, so that is why we selected Dobitsch's wavelet. And why DB8? There are many levels of Dobitsch's wavelet, DB2, 4, 8, 16 in the order of 2. But why we selected DB8? For this, we compare DB2, DB4, DB8, we applied at selected points, and what we observe, dB8 has the more correlation with the original signal as compared to the other levels. So that's why we selected dB8. So this is the threshold. Generally in the ultrasonic testing, we use soft thresholding with universal threshold. And then we plot the normalized amplitude characteristic with the distance, scanning distance. So this is the scanning distance. And then for each A scan, we find the normalized peak-to-peak amplitudes, and we can see. Then minus 3 dB threshold is the most common as a decision level for the guided wave testing. So we applied minus 3 dB threshold, and then we see the 81 mm defect is observed as 89.5 mm. But it is quite good because we are using only a single scan. We are not using the full C scan. And then location of the defect, original location was 75.5 mm. And here at least we can observe 74.5 mm. Then we applied the two-dimensional fast Fourier transform to filter out the reflected waves from our B scan. So this was our experimental B scan. So we see the reflected waves are filtered out after two-dimensional fast Fourier transform. Then what we do, we selected 2 points, at least 2 points at fixed distance. Here in the defect-free region, 2 points, and in the defective region, 2 points we selected. Then we applied the variational mode decomposition technique. So we have the 4 signals, 2 signals in defect-free region and 2 signals in defective region. And then we apply the variational mode decomposition techniques. In this way, we can clearly see IMF 4, 5, 6, they have the correlated noise, so which can be suppressed. How we did this? We cannot just see, okay, this is the noise, we have to eliminate. No, we have to find the power spectral density of each mode, IMF 1 to IMF 6, and then compare with the original signals in each case. Then what we found, that power spectral density of IMF 1 and 2 in each case are more similar with our original signals. So that's why we selected IMF 1 and IMF 2, added up and regenerated the signal. So after regenerating the signal, we applied the Hilbert Transform to find the instantaneous amplitude characteristics. So this is the instantaneous amplitude characteristics. In the defect-free region, there are 2 signals, S40 and 60, and similarly in the defective region. Okay, after applying the minus 3 dB threshold, we can clearly observe the time interval between 2 signals in defect-free region and also time interval between 2 signals in defective regions. So we have the fixed distance 20 mm and we have the time interval, so we can find the velocity of ultrasound wave in defect-free region and defective region as well. To compare the results, we developed the semi-analytical semi-finite element method. So these are the material properties for GFRP, glass fiber reinforced plastic, and these are the thickness of layer. Although thickness of the real sample was variable in the defect-free region as well as in the defective region, but in the finite element method, phase velocity dispersion curve, we cannot use the variable thickness. So the thickness in the defect-free region was 22 mm and in the defective region was 3.5 mm. Then we generated the phase dispersion velocity characteristics. So our interest is only on the A0 mode because our receiver was the contact type working in the thickness mode, which was more sensitive to the out of plane radiations. So that is why we have to just we are interested in the A0 mode. So we see the velocity is in the defect-free region is 1253 and in the defective region is 745. So these are the list of results. So we see the size of and location of the defect. So error is less than 11%. But in the phase velocity, we see the error is more. But it is because in the real sample, the thickness of the structure was variable. but in the modeling, we cannot take the variable thickness. So we have to take the fixed thickness. So that is why the result. But still we can see the difference between the phase velocity in the defective and defect-free region in both cases are approximately same. So in other experiments, we also performed by the two contact type transducer, and also we use the air coupled transducer in non-contact manner to verify the algorithm. So finally, these are the conclusions. So the experiment was performed using low frequency ultrasonic system in order to extract the disbond type defects on the wind turbine blade. Discrete wavelet transform with amplitude detection technique was applied to locate and size the defect. Later on, two-dimensional fast Fourier transform, variational mode decomposition, and Hilbert transform was applied to find the phase velocity and time of arrival of the ultrasound waves. The two contact type transducers and air coupled transducer was also used for the experimental investigation of other defects. And then signal processing algorithm was validated by analyzing different size defects. Thank you.
Okay, as suggested, we have some minutes to questions because we have time enough to hit. Any questions, please?
What precisely was the defect that you had? I don't know if I missed that. What kind of a defect? Did you have a delamination?
Yes, it was disbonds. Disbonds. Yes. Disbonds created by the milling process, mechanical machining process.
So you had a delamination between, a separation between
the layers and anywhere, yes.
Not anywhere.
Yes, anywhere in the thickness of the structure, anywhere.
But you had it in a specific place. You put in, what did you do? You put in Teflon? How did you put the D-bond in? How did you get the D-bond in the structure?
I did not, but it was performed by the milling process, mechanical machine that is called, by the provider who provided the sample. Yes, it was in the structure between the layers.
Okay, milling?
Milling process, it is called milling process.
No, I know
Yes.
what milling is, but I mean, you can't go inside the structure and do milling, you'll damage it from the outside.
Yeah, but it was inside. It was created by the provider, not by us. Yeah, they created like this, and then if the sample was specifically prepared for this.
Okay, and so how, I think you said you measured it to be the size of about 85 millimeters or something like the previous slide.
Yes.
And so from the waves, how do you, maybe you could put that back.
Sorry.
Okay. And go back to that slide. It was the one before the end, I think.
Yes.
No?
Please.
Another one?
Yes.
Here.
Yes.
Where you have 89.
Yes.
How from your results, where you're measuring velocity, I think you said you're measuring amplitude, how from those results do you determine the 89.5? How do you determine the size from the results that
Yes,
you're
from the results. It is in the slides. It is.
Okay.
In the back. Back, please. Or back more. One more. Yes.
Just a second.
Wait.
Here is. You can use the pointer.
Yeah.
You see the size?
And the location as well. First location, 74.5.
The location on the right-hand side is much more off, of course. So
Yeah.
you just happen to pick the left-hand side.
Initial
and then
location, yeah, it is the initial location of the defect from the receiving transducer. Starting position of the receiving transducer, 74.5 mm. And then this is the size of defect.
Yeah.
Okay, thank you.
Okay, I have one question also. Is in continuing of the last question. Okay, you assume the producer put a lamination in, and this technique is only valid for lamination Or by other words, what is the limitation of this
Okay,
technique? Because composite materials, sometimes you should combine different techniques to have a...
Yes. The limitation of the linear ultrasonic testing is like the size of defect. The size of defect, what we can measure depending on the operating wavelength. If defect size is less than lambda by 4, we cannot estimate by this technique. For this purpose, there is a non-linear ultrasonic testing combining with the peridynamic theory. I am not working on that, my colleagues are working, but we can estimate the cracks also.
The cracks
Yes, from the peridynamic theory, but is still not validated by experiment, only by modeling.
Okay, and only, for example, the cracks in the matrix could be appears in different zones and directions. You can obtain good results, good confirmations, good positions of the cracks in different...
I am not working on the. I am not working on this. Yes.
So in your complete identification scheme, you basically have like a first question whether or not you can basically identify the defect already on your wavelet analysis, and if not, then you go to your Fourier part and then...
Yeah, it is an algorithm. Yes.
Yeah. So why wouldn't you? Didn't you also check like how this looks, how well you can identify the defect?
No, because
if you this.
Yes. Because in the composite structure, because the guided waves are the dispersive waves. So they have the, for example, S0 mode means in plane in the direction of propagation. They have in plane and, for example, perpendicular direction of propagation, and they have out of plane modes. 3 modes, which is called S0. Symmetrical in the direction of propagation, A0 mode, out of plane, asymmetric wave mode, and also shear horizontal mode.
Yeah.
So we have 3 modes. And when for example, the guided waves passes through the layered structures, the modes can be converted.
Yeah.
So that's why from the phase velocity sometimes cannot be measured from the 2-dimensional fast Fourier transform, which is quite common to measure the phase dispersion curve. But it is not possible. So that is why we have to filter out the reflected waves and then consider only the directed waves, and then we apply the VMD and HT to estimate the time of arrival and phase velocity.
Okay, I don't see how that's an answer to my question, which I didn't finish.
No, you told why you apply this, right?
No, that was not my question. I haven't finished. So I was thinking, you do the filtering basically in your second part. You do the filtering.
Yes.
You apply that, and then you come back to your wavelet transform.
Yeah, first part it is okay. First part.
Wouldn't it improve it? Because you put in basically knowledge on you then know what kind of waves that you send into your signal, and so you pre-filter it, and then you do your wavelet transform. Wouldn't you get a better fidelity? Of
wave of interest was only the A0 wave out of plane, because receiver was the point type thickness mode, inverting thickness mode, so which is more sensitive to the out of plane radiation. So our focus was only on the out of plane waves. Out of plane waves. Then we applied the DWT for denoising to extract the size and location. But for the DWT, we cannot. DWT has many wavelet family, many spatial filters, such as Dobbechies, Haar, depending on the requirement. So we have to compare each technique which is more useful for us. Then we selected Dobbechies, then we selected BB8. There are many levels.
That's how you explained, yeah.
Yes.
I still think that the combination of the two techniques can give you some gain. Okay, but okay, good.
Thank you.
Thank you very much.